I'd like to introduce Christina Yu, who'll be talking to us about some network inference from linear to low degree polynomial models. The time is all yours.
Thank you so much. I'm really excited to share this with you. It's my first time talking about it, so I'm really eager to get feedback and thoughts from you all. So I'll start with a little toy example. So suppose you're working for the New York Department of Health, and you want to run a public health campaign to encourage people to wear masks at the peak of the, or hopefully before the peak of the COVID pandemic. And you want to, you solicit for a set of ads that, various creators propose, and you want to ask which ad is most effective. So ideally what you want to do is kind of estimate what I'm going to refer to as a total treatment effect. It's the difference between these two hypothetical scenarios where suppose I have some billboard space and I can choose to put one ad up, and everyone, when I put that ad up, everyone sees that ad. So either everyone sees this particular ad for public health ad for wearing masks, or some other unrelated ad, which I'll call the control. And what we want to estimate is this total treatment effect, or the average difference in the total outcome, where, for example, total outcome might be something like how many people are wearing masks after the treatment versus how many people would have worn masks anyways, whether or not they saw the treatment. And so a naive thing you could do is to say, well, nowadays I can do online ad campaigns. Why don't I run an A/B test online where there's some random traffic, and every user that arrives, gets shown an ad, either the treatment ad or the control ad, and then I measure the outcome. Let's say maybe through whether they respond on Facebook to like putting some pro-masking symbol up on their Facebook page or something. And so to introduce the notation I'll be using here, the individual is kind of indexed by I. The treatment, so the variable zi is going to be 1 if the individual I gets a treatment, and the variable zi is 0 if the individual I is placed in control. And here, this function y sub I, this is going to be our potential outcomes for this individual, and it's a function of whether or not this individual got the treatment, right? So y sub I evaluated at 1 is the outcome if the individual got the treatment. Y sub I evaluated at 0 is if the individual got control. And the naive thing to do, and a critical assumption that I kind of made already in the notation here, is that I've assumed the outcome only depends on the individual's own treatment, which is called the stable unit treatment value assumption. And so I've already made that assumption even in the notation here, the fact that this potential outcome is only a function of the individual's treatment. So under this case, the total treatment effect would be the same as the difference between these two quantities. Again, the average over the all outcomes, if everyone was treated, minus average over all outcomes if everyone was not treated. And a naive thing to do, or just a simple thing to do, a natural thing to do, maybe I'll call it a natural thing to do, is to compute a difference in means estimator, where I would just compute the, after I do this randomized experiment, I compute the average outcomes amongst all individuals that were assigned to treatment minus the average outcome of all individuals that were assigned to control. And randomization is important to get unbiasedness and to kind of break any confounding effects, because you're truly running a randomized experiment, so you know that there's no relationship between how an individual was assigned and their outcome. And but this critically relies on this SUTVA assumption, so the stable unit treatment value assumption. And so in this talk, we really want to focus in on how to deal with network interference. So what if an individual's outcome is a function of the treatment of his or her neighbors? So for example, here, let's say this grandpa is wearing a mask, and it could have a negative effect on this teenager boy on the right, but maybe a positive effect on the neighbor on the left. And the issue is now, once you introduce this network interference, you have to be very careful. A lot of the classical results, do not hold. And so, just to be clear about what the challenge is, now once we introduce network interference, we have to kind of update the notation. So the potential outcomes function here, yi, is now a function not only of my treatment, but also the treatment of everyone else. So here, the total treatment effect now is the average outcomes, the difference between the average outcomes if everyone's treated minus everyone's in control. But what happens is that when I randomly assign individuals to treatment and control, what I really observe, what I measure as the result of the experiment is the outcome of individual if they're treated and whatever happened to be the treatment assignment of his or her neighborhood. And so, in particularly, if the treatment assignment of his or her neighborhood does not fully match the individual's treatment, then that means the observed outcome is not either of these outcomes that we want to observe that actually form our estimate. All right, I guess any questions about the setup? And so without further assumptions, on the model, the best you can do is to look at estimators that are limited to only use information measured from the sets of individuals for which the individual and their treatment, their entire neighborhood get the same treatment. And so you're looking for individuals where the individual and all of its neighbors are assigned to control, or the individual and all of its neighbors are assigned to treatment. And that guarantees that the measured outcome is indeed one of these quantities in your estimate that you want to estimate. But the limitation, as you can see, is that you do lose statistical power because there's only a few measurements that you're even able to use after you run the experiment. And so, what often is done is actually to think of clever ways of designing randomized designs that help to boost up the probabilities of those events. But that can be actually computationally challenging for complex networks. And so, yeah, it is still a very kind of interesting challenge to deal with. So let me guys start stepping into the results. First, I'm going to set up a little bit of notation. So again, I'm going to use a potential outcomes model where y sub I denotes the outcome of individual I. Under SIDFA, the degrees of freedom in the model is just 2 times n, because for each individual, I have to define this function that just maps from a binary treatment or control to an outcome. But under what we're going to assume is neighborhood inference, meaning my outcome is only a function of my treatment and the treatment of a neighborhood of individuals around me, the degrees of freedom of my potential outcomes model is now 2 to the d times n. So you can see you get an exponential blow up in the complexity of your model. And on the other hand, the total number of observations, if I ran a single experiment, no matter how clever I am, I can only get n measurements. So 1 measurement from each individual. And the goal is to estimate the total treatment effect. And kind of the very minimal assumptions that you need is, actually I've already made it here in this, here I already imposed a neighborhood interference assumption. There's ways of generalizing this type of assumption that the idea is that if I want to measure the outcome of an individual under the event that everyone is treated, when I'm run an experiment and obviously not everyone is treated, I need to have some events under which the outcome is still the same. So under a neighborhood interference assumption, it's saying that if at least my neighbors are treated, then my measured outcome is consistent with what would happen if everyone is treated. And there's generalizations of that concept. And so to give a baseline, I just want to say what would be the first thing you might want to try. And this is so here I'm just using a Horowitz-Thompson estimator. It's an inverse propensity score estimator where here I'm multiplying by the indicator function of whether or not this individual I and its neighborhood are all treated, and I'm dividing it by the probability of that event. And I'm subtracting off this, again, indicator of whether the individual and all its neighborhood is not treated and divided by the probability of that event. I'm going to assume under also the most naive randomized design is Bernoulli design. So each individual is treated independently with probability P. If that's the case, then this expression for the probability of everyone being treated or in control kind of simplifies to this product. And you can calculate the variance. So this is an unbiased estimator, first of all, because of the by construction with the inverse propensity scores. But the variance here, you can see it scales with P to the D, and D is the degree of the node. And so it has an exponential blow up in the degree of of the individuals in the graph, and that ends up being very costly. P is yes. Here I'm just going to assume uniform. Yeah, uniform. So there's definitely smarter things you can do, but here I'm just starting with the very first thing you could try, which is uniform Bernoulli. So a natural question is, can we do better? And there's actually quite a lot of work in this space, and I'm really going to breeze by it very fast. But I'm going to classify them into kind of two categories. One I'm going to call nonparametric approaches that most of them focus on designing clever randomized designs that try to boost up that probability that you get to observe individuals and all their neighborhood in the same treatment or control. But the solutions depend heavily on the graph structure. And so, for example, one common assumption is that you have fully disconnected groups. So this is reasonable in many settings where, let's say, you have a type of effect where effects can only happen within households and there cannot be effect across households. This would be a reasonable assumption to make. And then that would allow you to say that, well, because now I have like fully disconnected households, in some way I can almost treat each household almost like a unit, right? And another approach is to use graph clustering. So imagine I have a network here. What I would do is I pick a set of individuals that are hopefully far-ish apart, and then I kind of I cluster the graph by assigning each individual to the closest cluster center. And then once I have these clusters, then I randomize over the clusters jointly, meaning each one of these clusters gets assigned fully to treated or fully to control. And what that does is it makes sure that any individual that's in the interior of the clusters, their treatment and the neighbor's treatment are always aligned. And that makes sure that I get, hopefully I get more informative measurements, right? And the kind of, I guess the comment I want to make is the clustering approaches, they can be computationally costly, and they do kind of hinge on very specific properties of your graph. So you're assuming your graph is clusterable, and that may be true, it may not be true, and and so yeah, in this talk I'll be looking for something a little bit more general in terms of graph structure. Another approach that I'll bucket a large class of approaches into is what I'll call parametric approaches. And these are settings in which we impose assumptions on the model such that kind of reduce the degrees of freedom of the model, such that the degrees of freedom of the model are significantly smaller than the number of measurements. So our number of measurements was n. We assume a simplified model. Let's say the simplest one is, suppose my outcomes is linear in the number of my neighbors that are treated, right? So in that sense, I have some covariate, it's the number of neighbors treated, and I have like one parameter I need to estimate, which is the coefficient of that, the slope of that, right? And in that sense, in that case, you can imagine that it's actually fairly easy to estimate. You can use a variety of regression style methods. You can also make the model a little bit more complex, use machine learning methods. But the key limitation is that you have to start with a class of models that where the parameters in your model are like significantly smaller than n, so that you can actually fully identify it. And as such, it also can be more fragile to model misspecification. All right, and one last comment I want to make is that pretty much all the approaches above, they do require at least approximate knowledge of the network, if not complete knowledge of the network. So if I want to do a kind of a clever cluster randomized design, I need to know the neighborhood. If I want to fit a regression style, a model, I need to also measure, I need to know how many neighbors are treated of this individual, so I need to know their neighborhood as well. So that's one thing we're going to want to deal with in this talk today is what happens when you don't have knowledge of the network. And the other comment I want to make is that the kind of results that I'm going to talk about today is looking at a non-parametric setting. So we're going to have a class of models in which the number of parameters is significantly higher than your measurements. So you cannot expect to fully identify. So you cannot use machine learning methods. However, we're not going to rely heavily on graph structure. Instead, we're going to think about, can we impose model structure that and figure out how to exploit that model structure, but not so restrictive that we move into the parametric world. So that will become explicit in a bit.
I'm wondering if you could clarify a little bit what you mean by parametric here, because sometimes I have like a functional form on the outcomes, and I assume that the coefficients maybe are shared across all the units, but sometimes the coefficients have the subscript I. And in the one case, maybe they both look like structural, but one of them looks non-parametric and one of them looks parametric.
Yeah, and
these kind of approaches do these not have little i's, or do you think that even little i's are considered parametric?
So the parametric ones do not have little i's. So it'll be something, or maybe instead of little i's, it might be something like my coefficient is a function of my covariates and my covariates observed. And so maybe I cannot have a separate parameter for every individual, but I'm allowed to have separate parameter for each group of covariates. But then I need coverage and that kind of stuff. But that's exactly the style of model we're going to look at actually. So great. So our quick question is: in the presence of network interference, does there exist a simple and efficient solution for estimating total treatment effect that does not critically rely on the knowledge of the network structure? However, our solution is going to require imposing some kind of appropriate model assumption. So wait for that. So the quick preview of what we're able to show is that, so there's two parts of our assumptions. The first part is the first line. So assume we have knowledge of the average baseline. I'll comment on that in a moment. So this average baseline is the average outcome under the control, purely control. Then if I use this Bernoulli randomized design, so I could really just take each individual, independently assign them to treatment or control, measure their outcome, and then construct my estimate by taking the average over all the observed outcomes, minus out the average baseline, and then scale it by 1/p. And so this estimator, I'm going to say plus, here I've hidden it still, a suitable model. So that I'm going to have explain an assumption under which this estimator is unbiased and its variance scales as d squared over p times n. So the kind of scaling with the degree is polynomial, or I mean, also just squared, simple one. And we will not need to have assumptions on the graph. And so a comment on the first bullet point. So that may be something you don't want to assume. I'm going to actually mention at the very end that we can actually relax that. But for now, let's just say, when could this be reasonable? We could have estimates of the average baseline from historical data or pilot surveys, and this is fairly easy to collect this data before the experiment begins because it doesn't actually require any experimentation, right? So we're only measuring something passively about the control before, but it does imply that the outcomes before you run the experiment and during is kind of the same. So it doesn't allow for time fixed effects. Okay, so now I'm going to tell you the model. So of course, this is the critical piece. What model makes this work? And here I'm going to look at a model that I'm going to call it a heterogeneous linear outcomes model, where your outcome is a linear functional of the treatments of you and your neighbors. So in particular, it's the sum of an individual baseline effect, that's alpha I, and then an individual direct treatment effect, that's going to be beta I, if I was treated, my direct effect on me. And then for each one of my neighbors, there's going to be a coefficient gamma ki, which is if my neighbor k was treated, what's their effect on me? And so the most critical part of the assumption is these network effects are additive. That makes they're additive across my neighbors. And so you can think of this model as, you can write it in matrix vector form, where the outcomes is equal to this vector of the baselines plus this matrix. This matrix has the betas on the diagonal and the gammas on the off diagonal times the treatment vector. And another way to visualize this model is to think of a graph here on the right, where I have alphas are kind of labeled at the node, and then every edge, the self edges have a label, which is the betas, and then every edge between pairs of nodes is has the weight, which comes from the gamma. And so when an individual is treated, I'm gonna highlight it red, and that means all the edges that are outgoing from that individual get also highlighted as red. And the measured outcome now is going to be, let's say the measured outcome at node 3 is going to be its baseline alpha 3 plus the sum of all the weights of incoming red edges. So any edge that is activated, or I'm calling it activated or red, it means that that the source of that edge was treated. So let me tell you why I think this model is a good one. First of all, it does allow for full heterogeneity. So as Chris mentioned, here's the alphas, the betas, the gammas, they all are kind of indexed. And so the total number of parameters in this model are 2 times n plus the number of edges. That is clearly more than the number of possible measurements. So that's why I call this a nonparametric model, because you can't, even as you grow the size of your data set n, your model complexity grows along with it, so that you never are in the setting where you can fully identify the model. Also, this model can capture endogenous peer effects such as contagion. What that means is, if you have a setting where my outcome is actually affected not by other people's treatment, but by other people's outcomes, but in a linear way, you can kind of take this linear relationship, write it as a system of equations, solve the system of linear equations, and you end up getting kind of a model that looks the same as the one we had in the top, but now with a different graph structure. In particular, if you had a sparse graph on this line, you might end up getting a fully dense graph on the bottom line, right? So a linear outcomes model, it can capture things like peer effects, but in contagion, but you have to keep in mind that it changes the meaning of the graph. And you can easily add independent measurement noise as well. Okay, so let me tell you why this result works. So again, I'll summarize the results and I explain the intuition. The result is that given knowledge of the average baselines alpha bar for any randomized design such that the marginal probability of treating an individual is equal to p. So again, there's some kind of uniform or balanced condition I need. Then the following simple estimator, which is the one I described earlier, it kind of does this simple scaling by 1 over p of the average total outcomes minus this alpha baseline. This quantity is unbiased, and I'm going to call it an efficient estimator, and I'll explain to you why why my interpretation for the variance is an efficient one for any network under the heterogeneous linear outcomes model. So critically, I want to comment that one, the randomized design is really easy. Bernoulli randomized design, you can't get easier than that. 2, computing this estimator is also super easy in that it doesn't require me to know knowledge of the network. 2, it didn't even actually use the realization of the treatment vector, right? I just did a naive average over all the outcomes. I didn't even weight by if it's treated or not. So this is like a really easy estimator to compute. So let me give you the intuition for why the result holds. Actually, it's very easy to see from the graph. And so once you think, so for this heterogeneous linear outcome model, when you view it as a graph, you can actually think of the total treatment effect as the sum of the weighted edges. So in particular, if you write out the total treatment effect, subtract out the baselines, right, then you get exactly the sum of all the self edges and also all the edges across. And treating an individual activates its outgoing edges. And the estimator, when you write it out and rearrange it a little bit, you can show this estimator is nothing but the sum of these activated edges. So I'm going to rearrange this expression a little bit. And now I've written the estimator. It's actually exactly equivalent to this expression where this term in the parentheses, I'm actually going to call the influence. And so in particular, it's for Zi, individual I. If he's treated, the coefficient, the thing that's multiplied in front of Zi is beta I, the direct effect of the individual being treated, plus the sum over all individuals K of gamma IK. So there is actually a transpose happening here. So gamma IK is representing the network effect that individual I has on individual K. And so what this influence parameter is, it's the sum of the outgoing edges of individual I. And so what this means is that under this model, you can reduce estimating total treatment effect to just estimating some population mean for a super simple model. In particular here on the left, in our original model, you can see the total treatment effect is this quantity here. If I relabel this thing in parentheses to the influence Li, Then on the right, it's just this scaled average of the LI across the entire population, the influence terms across the population. That's the estimator, sorry, scaled. And the estimator kind of estimates it for every individual that's treated. The quantity that I want to estimate is just the sum of the influence terms across the entire population. So you can think of on the left, you kind of have this complicated graph. Oh, it's not complicated, a simple graph picture where you can see by treating a node, I'm activating its outgoing edges. But what I'm measuring is like my treatment activates outgoing edges, but my measurements measure incoming edges. But it's okay because when I sum it all up, I'm just summing activated edges, right? And so it's kind of the same thing that's happening in the picture on the right, where I have just a population. Each individual has some quantity Li, and then I sample a subset of the individuals, a p fraction of them, to observe, and then I use the fraction that I sampled to estimate the mean of the whole thing, right? So on the right-hand side, we just reduce to literally the same, like estimation of a population mean that is like super studied and everything is independent, right? There's no network inference on the right. So I guess the punchline is that given baseline estimates, network causal inference is as easy as estimating a population mean when you have linearity. So you can show unbiasedness, and you can calculate the variance, again, using this relationship. And so my comment on why this is the efficient estimator, because if I was in this simple setting on the right, of course, the best thing I can do if I have a population I'm trying to estimate the mean, I sample a subset of them, and then I estimate the empirical mean. Like that's the efficient thing to do, in that you can't really do better than this, 1 over Pn scaling in terms of the variance.
The variance depends on the outcomes, or is it?
It depends. It depends on the inherent variance in these influence terms. L.
Variances of the L's because they're
they're actually not overlapping because I'm assuming in this heterogeneous linear outcomes model, I have a directed graph. So the edges, they're directed, and in that sense, the LIs are the outgoing edges. So the outgoing edges are not overlapping.
But one node has. Okay, so you're assuming the edges are independent?
I am assuming the edges each have an arbitrary weight, but they're not treated independently in that the node are the ones that are treated. So the edges outgoing from the same node are all coupled because that node is treated or not. And so every edge coming out from the same node is coupled.
But the outcomes of multiple nodes are going to be correlated.
Yes, so the outcomes of multiple nodes are correlated, yes.
So your estimator will have cross terms that have to show up in a variance calculation.
Yes, but the nice thing is that it's because you can rearrange so here is how you calculate your estimator. It's by summing over the y's, but I can rearrange this estimator and rewrite it. It's exactly equivalent to, so I can't actually compute the influence parameter. I don't know what it is, but the estimator, what it computes is exactly the same as what I would have computed if I knew the influence parameter, and I only summed the influence parameters for individuals that were treated. Does that make sense?
I think to stop a quick, sorry. Please.
Well, I was just wondering how you actually calculate the variance because the expression you had was in terms of the L's, but maybe that was.
Oh, yeah. Oh, sorry.
I think we can move on if we want to move on.
Okay. Well, yeah. All right. Well, I'm going to move on, and maybe happy to take that question because, yeah. So, but I think the key idea is that actually, you can analyze everything as if you were analyzing the model on the right. You cannot actually calculate the model on the right because I don't know. I don't for my data. I don't know my LIs. But when I sum them all up, the outcomes up, the sum of the outcomes is actually the sum of the L's of the activated nodes, treated nodes.
Question. It seems like this doesn't really need the graph structure, as you said, and it should transfer to other constraints like low rank, assume the matrix is low rank, or anything that constrains the complexity of these linear functions. Should give you some result where instead of the degree you get rank or some other thing. So.
Yes. So actually, maybe I'll move on to. There's some extensions, and I have partial answer to that, and I think maybe more later. But we are able to extend it beyond linear. we can extend to low degree polynomials. Low rank, I think, potentially, but
Talking about linear, but like a constraint on
Oh.
the matrix other than locality.
oh,
Let's say rank or
okay,
something,
I
like
see what you
any
mean.
matrix constraint that says you don't have like anywhere.
Yes. Okay, that's a great question. So I thought about that, and I would love a result like that. The thing that I'm not sure how to get is that at the end of the day, my measurements, I only have n measurements, and so I somehow have to critically use the randomness of the randomized design in my matrix estimation. And right now I don't know of good techniques that can do that for matrix estimation. But I think that's a really great question. I would love to figure that out. Yeah, so I'm happy to end on this slide. I guess my comment was that we do have extensions, one beyond linear to low degree polynomials, and we also do have extensions when you actually don't even know alpha bar. So I sort of explained the intuition is cleanest in the one I explained, but when you don't know this alpha bar, the baselines, there is also something you can do where you can construct an estimator. You do need to know the graph there. But you're able to get an estimator that scales like 1/Pn, and there's a polynomial dependence on the degree. Yeah, so I guess I'll leave it at that. Happy to take questions.
Great, let's thank the speaker. One or two short questions here.
Another question, which is, are you assuming that the Y's are independent but for the interference effect?
What I'm assuming is that like all the randomness in the model in when I compute bias and variance is purely from the randomized design.
Okay.
I'm not assuming any probabilistic model on the weights or anything, so they're fully arbitrary.
Okay.
So I had one question, and maybe as I ask it, we can switch speakers here. The question I had was, if we know the baseline, so if we know the sum of the y zeros, and we said, oh, I don't have to know the graph or anything, I have a very simple type of estimator, then the variance can be bounded. I know of a design and an estimator that has variance 0. I must have missed something, because I could just assign everyone to treatment, and then I observe all of the treatment. So if I have all the baseline, I'm done, and the variance is 0. What have I missed here?
Oh, I'm kind of assuming that if you have a budget on your treated fraction. So I only give you a budget that you're only allowed to treat in your experiment. So here we were thinking, the collaborator I worked with at that time was consulting for LinkedIn experimentation platform. And the idea is that, I want to test something, and LinkedIn says, when you're running these randomized trials, like at most you can test on 2% of my traffic. Like, I don't want you to, treat everyone.
Okay.
Yeah.
That totally clears that one up. Awesome. Great. Thank you. And let's thank Christina.